All right, let's dive in. We're about to pull back the curtain on this incredible chemical reaction that is, seriously, happening everywhere, all the time, right under our noses. We're talking about the hidden dance of redox, and it all kicks off with a pretty interesting question.
Now, it totally sounds like a riddle, doesn't it? I mean, think about it. A battery powering your phone, a piece of metal slowly turning to rust, and a crackling fire. On the surface, they feel like they're from completely different worlds. But here's the secret.
That's it. A single, super elegant chemical principle is the engine behind every single one of them. And that's exactly what we're going to unpack right now.
To really get this, we need to meet the two partners in what I love to call the chemical dance: oxidation and reduction.
You know, chemists are all about efficiency, so they just smashed the two names together and got redox. The big takeaway here is that it's not one or the other, it's both. They happen at the exact same time always.
It's just like dancing, right? You can't do a tango by yourself. You always need two partners. One gives something, the other takes it. They're perfectly in sync every single time.
So, how did we first figure all this out? Well, the whole story started with the most obvious chemical that scientists could see making big changes, and that was oxygen.
This is the classic, old-school definition. The perfect example is iron turning into rust. That's just iron oxide. The iron literally combines with oxygen from the air, so we say it's been oxidized. Pretty straightforward, right?
And of course, the other side of that coin is reduction. Think about taking that rusty iron ore and heating it up in a furnace to get pure iron. What are you doing? You're ripping the oxygen off. You are reducing the ore. And this just shows that perfect balance. If one thing is gaining oxygen, something else has to be losing it. You can't have one without the other. They're locked in that chemical dance together.
But the oxygen story isn't the whole story. It's a great start, but it's just one version of the dance. The real action, the deeper truth, well, that's not about whole atoms, it's about tiny little electrons. Okay, so this is the modern, more powerful definition. Just forget about oxygen for a second. Anytime an atom or molecule loses one or more electrons in a reaction, we say it's been oxidized.
And its partner, reduction, is simply the process of gaining those electrons. The thing that gets reduced is the one that sweeps in and grabs the electrons that the other partner just let go of.
Okay, I get it. Losing electrons, gaining electrons, it can be kind of tricky to keep straight in your head. But don't you worry, chemists came up with this awesome little trick to remember it.
Just burn this into your brain. Oil rig. Oxidation is loss. Reduction is gain. That's it. If you remember literally nothing else, remember oil rig. It is the absolute key to unlocking all of this stuff from here on out. It's your new best friend.
So what happens when a reaction doesn't even have oxygen, or when it's just not obvious who's losing or gaining electrons? Well, to handle every possible situation, chemists needed a universal tracking system. And that brings us to something called the oxidation number.
Think of it like a scorekeeper in a game. It's not a real charge, it's more like a hypothetical number we assign to an atom just so we can track where all the electrons are moving during the dance. It's just a really, really useful bookkeeping tool.
And to assign these numbers, we just follow a few simple rules. Like for any pure element all by itself, say a chunk of copper metal, its number is just 0. For a simple ion, its number is just its charge. And the most important rule, inside a regular neutral compound, all the numbers have to add up to 0. That's pretty much all we need.
And here's the payoff. If an atom's oxidation number goes up during a reaction, it got oxidized. Why? Well, it lost negative electrons, so its score becomes more positive. And if its number goes down, it got reduced because it gained those negative electrons. See how that works?
Okay, theory's great, but let's see this in a real reaction. Here we've got a piece of solid zinc reacting with some hydrogen ions, and what we get is a zinc ion and some hydrogen gas.
All right, let's use our rules and assign the numbers. That solid zinc, it's a pure element, so it gets a 0. The hydrogen ion has a charge of +1, so that's its number. On the other side, the zinc ion has a +2 charge. And finally, that hydrogen gas, H2, is a pure element again, so it's back to 0.
And now we can see the whole dance. Look at zinc. It went from 0 all the way up to +2. Its number increased, so it was oxidized. It lost electrons. And what about hydrogen? It went from +1 down to 0. Its number decreased, so it was reduced. It gained those electrons. See? The numbers make it all perfectly clear.
So whether we're talking about oxygen or we're talking about electrons, or we're using these oxidation numbers, we're really just describing the exact same fundamental process of redox. We're just looking at it from different angles.
This table just sums it all up perfectly. Oxidation is gaining oxygen, or losing electrons, or seeing its oxidation number go up, and reduction is the complete opposite for every single one. 3 definitions, one beautiful, elegant chemical dance.
Because at the end of the day, that's what this is all about. The movement of electrons is the movement of energy. It's what powers our bodies when we breathe, it's what makes a battery work, it's what makes photosynthesis happen. So next time you see something rusting away, or you light a match, you'll know exactly what you're seeing. You're watching the dance. The real question is, where else is it hiding in plain sight?